Magnetism. So Earth's magnetic field is generated by the flow of molten iron in the outer core. So the inner core is solid, iron nickel, and then the outer core is liquid, molten iron, and then that can flow around the solid inner core. And basically, if you have two metals that kind of move against each other like that, you can actually create magnetic fields. So that's how the Earth generates its magnetic field. This causes compass needles to point north, and at least our current compass needles would point north. Now, if a magnetic reversal happens, this happens when the flow in the outer core changes and Earth's magnetic field changes direction. So magnetic reversals basically up would be south and then down would be north instead of the other way around. This has happened many times in Earth's history. And the current magnetic field is what we consider normal polarity. So, in other words, north is up on a map, or north is at the North Pole, where we think about it, like we're in North America. The opposite field would be reversed polarity. Okay, so just to kind of talk about what we currently have, it's kind of weird to think about, but if the Earth had a bar magnet in it, the south pole of the magnet would basically be pointing to the North Pole. So I know it's kind of confusing, but if you think about it, if you want the North Pole of a magnet to point to the North Pole of the Earth, then the South Pole of the magnet would have to be up here. Why? Because the opposite pole is attracted. So the North Pole of this magnet is actually pointed to the south right now. So again, a compass needle would align to where the North Pole of the magnet is pointing up. Now in a magnetic reversal, this just flips. So you'd have the North Pole up, you'd have the South Pole down. Now if you did this, the South Pole needle on a compass would actually point to the North Pole at this point. So I know it's kind of confusing, but the big thing here is really just this flips. Okay, don't get too hung up on the north and south part of this, but you just have to remember that if you try to put two north ends of a magnet together, they will repel each other. If you put a north and a south together, they attract each other. So if you want the North Pole of your compass, if you want north pointing up on the compass, then you have to have it pointing towards a south pole of a magnet. But anyway, like I said, the big thing here is to keep in mind that this does flip directions, flips orientation. Now, the magnetic polarity time scale. So paleomagnetism is the study of the history of Earth's magnetic field. So paleo means old, magnetism referring to magnets. Now, how do we study this? Well, iron-bearing minerals like magnetite crystallize as lava cools. So the minerals behave like tiny compasses and align with Earth's magnetic field. Now, data collected here led to the construction of a magnetic polarity timescale, which is kind of what we have here. So we have sort of our current time here, and then we have a reversal. The yellow is reversal. We have a normal polarity, and then a reversal period here, normal, reversal, normal, reversal, normal, etc. So you kind of get an idea that some of these are longer than others. These don't happen at specific times or anything like that. There's sort of an average. And if you kind of notice, we're in a really long period of normal polarity right here. So we're actually kind of due for a flip. Now, magnetic symmetry. So the ocean crust is mostly basaltic rock, and basalt tends to have large amounts of iron-bearing minerals, which basically makes it perfect for recording these magnetic reversals. Now, magnetometers, which we talked about before, are devices that measure this magnetic field, and we tow these behind ships to record the magnetic orientation of the rocks on the ocean floor. Now, regions with a normal polarity and reverse polarity form a series of stripes parallel to the ocean ridges. So you have the ocean ridge here, and then you get these stripes that are parallel to that ridge. You also see the pattern of stripes is the same on either side of the ridge. So you have a normal polarity right beside the ridge now. If you go out a certain distance, you have a reversal. you go at a certain distance again, you have a normal polarity. And again, you go the same distance on either side of the ridge and you find the same polarity. So we have this symmetry of polarities here. Now, comparing patterns between ocean and land. So patterns on the ocean floor, patterns of magnetic reversals on the ocean floor were matched up to patterns that we found on land. And based on that, we were able to collect rocks on land, and then you can get the ages of those rocks, and you know those rocks are basically the same age as the ones on the ocean floor. So it's possible to determine the age of the ocean floor then from this magnetic recording. What we created here is what we call isochron maps of the ocean floor. Iso means same, chron refers to time. So an isochron is an imaginary line on a map that shows points that have the same age. Okay, so young ocean floor crust tends to occur near the ridges, like we have 0 to 0.7 million years here. As you get further away, it gets older and older. So this goes from 0 to 0.7 to 2.5 to 3.3 to 5 million years old. Now the older crust, again, is found along the deep sea trenches. It's found the furthest away from the ridges, or it's found along the deep sea trenches or near continents. So now to get an idea of a map of the ocean floor here and looking at the ages of these rocks, the reds are the youngest. So the youngest are occurring right along, this is the mid-Atlantic ridge right here. This is the East Pacific rise. One thing to note here is like this is fairly narrow here. So this is actually spreading fairly slowly. This is actually a really wide band of younger rocks. So this is actually spreading a lot faster than this one is. So you can kind of get an idea of the speed of these things by looking at the age of the rocks. But as you get more to the yellow, they get older, and then greens, blues, etc. So the youngest rocks are found right along the ridge. The oldest rocks are found near the continents. So there's about 180 million years old here. That's some of the oldest ones we find on the seafloor, unless we go over into, say, the Mediterranean Sea and stuff here. You start getting some older rocks. These are about 280 million years old. But again, for the most part, just looking at the main oceans, you have this nice pattern of really young to older to older to older. So the greens here are about 120, the yellows are about 60. Then you get down to the light blue here, and you're down to 180 million years old.